Hello dear students, and welcome to the second part of the subsoil investigation video. Now in the previous part we looked at different stages, or at least the name of different stages in a subsoil investigation. Now in this video we're going to have a closer look at each and every stages. Let's start with a desk study. As the name suggests, we sit on a desk and basically study. That the main purpose of this is to gather as much information as we can before we actually start doing the actual exploration. And often this desk study is often done during the proposal preparation stage, and what we're targeting to find is probable ground condition. Is it going to be a silty soil or sandy soil or clay soil or whatever? And then we are also looking for likely problems that might occur, that investigator might face, say for example access to plants and equipments and access roads and those sorts of things during a desk study. Some of the sources of information that can be consulted in a desk study are presented here. Soil maps are a very useful source of information. You can look at a soil map and have some understanding or idea what type of soil we might be encountering in there. Geological map will give us information on what sort of bedrock profile we are expecting, mining records, adjacent site investigation, and all the other sources can be consulted as well to gather as much information as we can. And sometimes experience, we can consult some of the people that has previous working experience in that particular area where we're targeting the subsoil investigation. They can be a valuable source of information as well. Now, once the desk study is done, the engineer or the geotechnical or subsoil investigator will go to the field and do a walk-around survey and do some of the visual tactile test. We learned in the soil classification when we were studying soil classification in a couple of videos ago. So they'll be doing some visual tactile tests as well. Now, during this reconnaissance survey, what we are targeting to find is, say, extra information on geology. Obviously, we'll be targeting to confirm whatever we have learned in the desk study. So we'll be going there and visiting the site and find out as much information as we can on the soil geology, soil type from the visual tactile test. We'll be also looking at likely construction problem, likely site investigation problem, access issues, if there is a water source available, or if there is access road, or how big it is, all these sorts of things. We'll be investigating or collecting information during this reconnaissance survey stage. Now, once that is done, just a quick note here, both desk study and reconnaissance survey, they're a very cost-effective way to gathering information. They're probably the most cost-effective stages of a subsoil investigation project. Now, once that is done, what we have to do, we have to go to the field and start exploring the ground. Some of the common methods we'll be looking at in a second, but the purpose of a ground exploration is basically what we're trying to find out is lateral and vertical variability or profile of the soil. What sort of stratification, what type of soil is in a particular layer, how thick that layer is, and at the same time we'll be collecting samples from different layers, and at some cases we'll be targeting or trying to look at specific targets. Say, if we know there has been a history of mining in a particular area, we might be looking for subsurface voids. Sorry, my lines are not very straight. Anyway, so subsurface voids or things like that, we might be targeting to find out during this stage. Now, some of the different methods, there are a number of methods commonly used for ground exploration. Test pit is a common one. Drilling, it's another very common method. Drilling is sometimes accompanied by some in situ testing, and there is a new or more modern technique that is coming into the market, geophysics. Now we'll be having a closer look at each of these ground exploration methods. Test pitting, as the picture shows, it's a very easy technique. If we don't have to explore too deep into the ground, we can just go there and dig a hole and look at the soil and collect samples from different depths. As you can see, this gentleman here is looking at different layers of soil, or looking at the stratification. And if we have to go a bit deeper sometime, we'll need a start of support like this. Now, test pitting can be a very easy technique and very good method to obtain detailed information on especially strength and stratification and pre-existing failure surfaces. So test pitting can be a very good method of exploring those. It's the very high quality block samples. When we're digging a hole, we can just cut a block of soil and then send it to the lab for testing. So high quality block samples can be taken, and equipment and personnel are needed. They're with reasonable cost, and we don't need very experienced or skilled personnel to dig a hole into the ground as well. So that's a good thing. Now, on the flip side, test pits, obviously, if you dig a hole before construction, that needs to be backfilled. Also, sometimes confined space or working from height restriction may apply. Now, test pitting, even though it's a very common or easy technique, it's not applicable to all the places, because in some cases we might have to explore ground condition up to, say, 10 meter, 20 meter, extreme cases 60 or 70 meter deeps. Now, we cannot obviously dig a hole that deep, so we have alternative. We call it drilling or boring. What we have to do, we have to just go there in the field and take an appropriate set of machinery. Say we have a couple of examples in here, cable percussion drilling, and sometimes we'll use augers. Go to the field, dig a hole and extract samples from different depths, and then send them to the lab for testing. Now, there are a couple of videos in here. You can see the YouTube links are shown. Feel free to click on them and watch them in your leisure time. Core drilling is another technique we can use to dig a hole, but this is not very common for soil. More often we'll be using that for cutting rock core samples or in a very difficult or hard ground conditions. So that's drilling and boring. On the pro and con side of it, drilling or boring allows samples to be obtained from much greater depth, as we have discussed. It minimizes disturbance to the ground. It's very important. Say we'll be digging a hole that is only, say, 100 mil in diameter, so the disturbance to the ground is very, very minimal. And we can use this in conditions which precludes our test pits. That is where we cannot use test pitting. Say, for example, very, very soft or very, very hard ground, we cannot use test pitting. In those cases, boring or drilling can be a very effective method. And obviously, it is much, 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 much quicker than test pitting. On the flip side, specialist equipment and personnel are needed, and drilling sometimes can be a bit expensive. Alongside drilling, we sometimes do what we call in situ testing. The standard penetration test is one of the very common one we do. It's basically digging a hole to a particular depth where we want to do the test, and then lowering a standard tube, and then applying some hammering force with a standard hammer and count the number of blows that is needed for a required amount of penetration. Now, higher the number of blows we need for, say, 300 mil penetration, stronger the soil will be. So that number, we call it blow count, and they're often correlated to strength parameters and some of the other parameters as well. In little more details, the standard tubing I was talking about, the standard diameter for the tube is 51 millimeter outer and 35 millimeter inner diameter. It's about 650 millimeter length. So let's say if I can draw it straight. No, probably I'll draw it in here. So it's about, let's say it looks like this. So that's the tube, and it has a reasonably thick wall. All these dimensions are standard. So whenever I'm doing a test in site A and site B, the results will be consistent, and it has a little cutter head, and all these dimensions are standard. And usually if you look at a tube like this, it will have graduation. Say it has 3 different sections, each of them 150, 150, 150, and the standard penetration number we call it N, or blow count, is the amount of hammer blow needed for the second 300 millimeter of penetration, and that is correlated to a number of different soil strength parameters. And while doing this standard penetration test, since this is a hollow tube, it will be collecting the sample inside the tube as well, and when you are extracting it, we'll be able to visually see the sample when it is on the ground. So that's a very big benefit of standard penetration test. We can do the testing in the field, and also can extract samples from certain depths, and that can be used either to do some field testing or can be sent out to the lab for more laboratory testing as well. Sorry, excuse me. Now, another common form of field testing is, we call it CPT test, or cone penetration test. As you can see in this picture here, it's a standard cone, about, I think its diameter is about 50 millimeter. There are other standard dimensions as well. What we do, we take a machine like this. Sometimes it can be mounted at the bottom of the truck as well. We set it up, and then we keep on pushing this standard penetrometer, we call it. We keep on pushing it into the ground and record the resistance, as you can see in here, at different depths. The cone has faced different amount of resistance, and based on this observation, we can correlate these resistances to number of different soil strength parameters as well. There is a video link in here in this slide. You can see. I'll strongly encourage you to go and click on this link and watch this video. This talks about advantages and disadvantages of CPT, that is cone penetration test and standard penetration test. These two are very common tests done in the field of geotechnical engineering. Now, geophysics, as I have mentioned earlier, is one of the newer technique that is coming into the market, still in its development stage, but I thought I should just include it. How it works is, you can see this cable running along, and attached to this cable are a number of geophones at different locations. And there is a steel plate in here, and this guy will hit it with a hammer, and then there is a computer somewhere in the background. What it will do, the hammer blow, it will create a seismic wave, and then that seismic wave will travel to different locations of geophones, and say, depending on the soil strength and stiffness and stratification, that seismic wave will travel to different geophone locations at very different speeds, and then that data will be converted into some sort of soil strength or soil stratification and some other important soil parameters. Now, so far we have talked about ground exploration and different methods of it. In this slide, we're going to talk about what are the spacing, or how many boreholes we need, or how many test pits we need to dig, what sort of spacing they need to be. Now, the spacing and then depth and all these sorts of things, they obviously depend on the purpose of the project, or what we are actually going to construct in there. See, if I'm going to build a car park, or if I'm going to build a car park and then I'm going to build a bridge, these two projects, they will definitely have very different load carrying characteristics or load carrying requirements. So the spacing and depth we need to cover during an exploration or ground exploration has to be very, very different. So here are some of the examples or some of the guidelines to set up spacings, but they are just guidelines. Sometimes we need to do more closely spaced or less closely spaced, depending on the site, depending on the project as well. So these are basically some guideline as a starting point. And as we have done some of the exploration, that will tell us if that spacing what we started with is correct, or we need to do more closely spaced, or we can see the variability is not that much, so we can do a bit less closely spaced exploration. So it's a very, very dynamic or continuous process. Now, during ground exploration, you have seen the SPT test, or there are samplers as well. We can extract sample, and sometimes they can come in a tube, and sometimes they come in bags like these. So these are obviously disturbed sample, and during ground exploration or drilling or boring, we sometimes extract samples in tubes as well. So if we extract the sample in a tube, it obviously retains its fabric or retains its structure. We call them undisturbed sample. And if the sample comes in a bag like this, we call them disturbed sample. And disturbed samples are only good enough for soil classification. So we can only tell how much silt or how much sand particles or what sort of plasticity it has, these sorts of information. But it's very difficult to tell from a bag of sample like this what it will be, its strength characteristic or how strong it is, because the strength of the soil obviously depends on the particle arrangement, the density, and all these sorts of things. And all those things have been lost in these samples. Anyway, we still can identify the soil type and extract lots of very useful information from bags of samples like this in the lab as well. So once the sample has been extracted, they will be sent to the lab. And here is a list of some of the very common tests we do in the lab. Sieve analysis, we have learned about it, or at least some of it. It's used for soil classification or particle size distribution, and some other tests as well. So we'll be having a closer look at some of these tests. I'll just briefly discuss it here, the reactivity test, because we don't have any other slides on this. Reactivity test is basically, this is more specific to Adelaide, I should say, Adelaide and Melbourne and some other parts of Australia. Expansive soil, we have heard about it, very high plastic clay they are. Now this soil, they shrink and swell very much, or too much probably, because of seasonal change in moisture. And if we want to quantify their properties, this shrink soil properties, we have to do some of these tests, say shrinkage test, soil test, and suction measurement. If we do them, we'll be able to quantify how reactive a particular soil is, and then from there, using this information, we'll be able to design things on reactive sites. So they are very specific to reactive soils, not done in all different soils, but these are some of the more common ones: sieve analysis, consistency, automated test, and direct shear test. Let's have a closer look at each of these tests. So sieve analysis, we take some soil sample and we pass them through a stack of sieve like this. This is just some example sieves in a stack, or in a standard stack there will be more sieves, a higher number of sieves. And once we have done that, we'll be putting it to a sieve shaker, and after the sieve shaker has finished its job, the soil will be separated into different particle size fractions, and using those fractions, or looking at those fractions, weighing them and plotting them in different curves, we'll be able to tell if that soil was well graded or poorly graded, and so forth. Now for some soil, let's say the finest sieve, if this is the finest sieve, we have 75 micron. See in here, micron. So 75 micron is approximately a little less than a tenth of a millimeter, and anything finer than that, say soil particles, can be up to 2 micron, even smaller. So it's very, very smaller. And if we reach at a level of 75 micron, it's very, very difficult to sieve, because the pore size or aperture size is very small. So the sieving becomes very inefficient. We have to sieve for maybe days to get anything passing through a finer sieve than 75 micron. If we want to know about the particle size distribution below 75 micron, what we do, we use an apparatus called hydrometer. This apparatus works on the principle that, like, what we do is we take some water in a hydrometer or cylinder like this, mix it with soil, and then shake it very well and let it settle. So what will happen, if the particles are a much bigger size, they will settle very quickly. If the particles are much smaller size, they will be taking time to settle. And we continuously measure density of the water at a certain location. And depending on those density numbers, we then extrapolate them or translate them into different particle size and their relative percentage. So sieve analysis is done up to 75 micron, and anything below that, we need a hydrometer analysis to find out the particle size distribution. Again, if you remember the behavior of soil or soil classification, the behavior of soil, the behavior of soil at these fine particles, or for these finer particles, are often controlled by its plasticity, not its particle size distribution. So even though this can do particle size distribution below 75 micron, this is not a very common test. We still do for some specific purpose, but you might not find that very, very common. Moving forward, Atterberg limit, liquid limit, plastic limit, if you remember. These are the apparatus I'm not going to discuss in any more details. These are the apparatus we'll use to find out liquid limit. This is called a Casagrande type apparatus, and this is called a Falcon apparatus. Both of them can do liquid limit, and this one can also do plastic limit test as well. The apparatus you see in this picture, we call it odometer. It's basically, we take a soil sample and put it between two porous plates and apply pressure and look at its deformation behavior. And information collected from this test often used in settlement calculation. Direct shear test, we have already talked about direct shear test. The process involves taking some soil sample and putting them in a box which has two halves, and then apply some normal load like that, and then push one half of the box, slide past the other, and observe how much resistance it is offering at this interface. And then we translate them to some sort of strength parameters. We call it cohesion and friction angle. We use term C and phi to denote cohesion and friction angle. Anyway, that's all we'll be learning today. In summary, we have looked at different stages of a ground investigation. We have also looked at different in situ testing, including CPT and SPT, especially CPT and SPT, and we also looked at some of the common laboratory tests. With that, I will say thank you. And here are some of the images that has been used in this video.